Well, good morning or afternoon, everyone, as the case may be. Thank you for joining us for this month's Director Seminar. The topic for today's seminar sort of arose as a result of a recent publication by members of a couple of NAI teams, both Ken Nielsen's alumni team and Vicki Meadows' alumni team, on work done on Snowball Earth, and particularly on the role that Snowball Earth may have played in the development of oxygenic photosynthesis. And in talking about this, we thought that having perhaps an even broader talk about new and emerging perspectives on Snowball Earth would be an interesting topic, and fortunately, we have somebody who's been spending a great deal of time doing that kind of work to present this to us. Tim Raub worked as both an undergraduate and a master's candidate at Caltech with Joe Kirschvink on Snowball Earth topics and has continued to do so. I might note, ironically, that Snowball Earth is one of the hot topics in astrobiology. Tim is now finishing his PhD at Yale, studying Earth's history and paleomagnetism of the Ediacaran period, and he is going to be talking with us about new and emerging perspectives on late Precambrian Snowball Earth glaciation. So, Tim, I will turn it over to you.
Thanks, Carl. Central to the idea, I think, of many astrobiologists is that perfectly normal uniformitarian geological processes, Earth system processes, can produce seemingly non-uniformitarian outcomes on a world where boundary conditions are sufficiently different from those today. So keeping that idea in mind, I want to review several recently published and ongoing studies probing links between Earth's deep geodynamics, its surface rock and ocean geochemical record, and its atmospheric chemistry, especially through Precambrian time in light of its glacial record. The classic idea of a Snowball Earth is familiar to all of us, in which if a mysterious forcing mechanism lowers the greenhouse effect, presumably by decreasing either the effect or the concentration of greenhouse gases such as carbon dioxide, and ice encroaches on the oceans to some threshold latitude, at some point it will run away, here in a classic one-dimensional energy balance model, leading to a Snowball Earth, a total ice cover scenario. The greenhouse return above the ice-covered oceans will eventually overcome the albedo cooling effect, and the catastrophic return to the ice-free state is presumed to be quick and dramatic. For more sophisticated models, Ray Pierre-Humbert and colleagues at University of Chicago have been among many GCM modelers who are considering the problem recently, and introducing ever more sophisticated ice dynamic considerations tends to make it both easier to enter a total Snowball Earth, and also possibly harder to leave it. But anyway, so the idea is familiar to many of us and exists for purposes of this talk in no more sophisticated a sense than the classical one-dimensional energy balance model. What I want to examine is the idea of Snowball Earth as one of three possibilities. Either the very same glacial process that we see in the Plio-Pleistocene record, the Permian record, the Ordovician glacial record, but on a world with different boundary conditions, as an entirely distinct glacial climate mode responsive to the Earth system to some unknown forcing, or as a continuum. As boundary conditions change, there's a whole range from hard snowballs in the very early Precambrian to modern glaciations, and we simply see a very broad, gradual response of Earth's climate system through time. David Evans formulated this view by tallying up all the paleolatitude estimates, either derived directly from the sedimentary record, as for the Cenozoic glacial record here, through the lens of paleomagnetism for the Paleozoic glaciations, where to different extents we have confidence in paleogeographic reconstructions, and through the paleomagnetic record of a rather limited data set for the Neoproterozoic and Paleoproterozoic glaciations, where at least two highly robust paleomagnetic signals indicated low paleolatitude for glacial deposits and a complete absence of high paleolatitude in the Precambrian time, as opposed to just the opposite situation for the Phanerozoic. Another way of looking at this and framing what I said in terms of our span of possible ways of looking at Precambrian glaciation is this time-space plot, and I'm trying to superimpose three different things here. One is the continental configuration, the paleogeographic style. So what I've done is estimated in yellow the surface area of supercontinents, at least the supercontinents that I think most Precambrian geologists would say have a good chance of having existed for, at minimum, the duration in geons indicated on the x-axis, and then taken the square root in kilometers of that surface area for each supercontinent, Kennerland, Oldest, Nuna, Rodinia, Gondwanaland, and Pangaea, converted the square root distance scale to a degree characteristic length scale centered on the equator, so that taller supercontinents are essentially larger supercontinents. And we also see rough estimates of the time intervals over which supercontinental amalgamation and orogenesis dominated in blue, leading into supercontinents, and supercontinental rifting and dispersal of fragments.
Could you define a geon? Could you define a geon, please?
Yeah. Geon is a convenient word that we can use to talk about a given 100 million years of Earth history. It's simpler than Precambrian specialists being able to throw around dates like 2316 plus or minus 7. We can talk about geon 5 events, and we mean anything from 500 million years to 599 million years. So here the Phanerozoic, geon 0 to mid-geon 5, involves Gondwanaland building into Pangaea, whereas the Paleoproterozoic saw the growth of the supercontinent Nuna, and really it's not clear whether Nuna ever decayed to nothing or whether it simply continued to grow into the supercontinent Rodinia, which famously fragmented amid many, at least 5 distinctly dated now, Neoproterozoic glacial deposits. So the question again is, are we seeing two distinct glacial modes where all Precambrian glaciations, denoted at minimum by the icicles hanging from 90 degrees at the pole down to some not necessarily quantitative estimate of their maximum equatorward extent, are these fundamentally different in Precambrian time, a snowball mode versus Phanerozoic time where they rarely encroached on the continents greater than about 40 degrees paleolatitude? Or are we seeing a shift where as life evolves ever more complexly, as the sun becomes brighter and hotter, as the atmosphere changes, we see a gradual decrease through time? Okay. The last part of the introductory information to keep in mind is the Hoffman and Schrag formulated or enunciated version of a snowball hypothesis, in which the entry into the snowball is catastrophic, driven by unknown processes, but again, presumably involving sudden drop in CO2, leading to catastrophic reverse, or rather positive ice-albedo feedback. And then it takes some long duration of time for volcanic outgassing to build up enough greenhouse forcing to reverse the Ice-Albedo Runaway, which happens equally catastrophically. The point is that during a snowball Earth, the Earth is cold, and this happens for a long time. At the end, you're hot, and the transition between cold and hothouse worlds is very quick. This is simple, and everyone is generally familiar with these ideas. What might lead to the catastrophic drop in CO2? Pavlov et al., astrobiology team members, noted in 2001 that presumably if the early Archean atmosphere were dominated by methane greenhouse gases to compensate for the faint young sun, then any introduction of oxygen, oxyatmo version, so to speak, into the atmosphere would lower the residence time of methane, and over some period of time, perhaps hundreds of millions of years, the Earth would have to readjust its fundamental greenhouse gas concentration response. And so this might lead to the Paleoproterozoic or Archean glaciations. This idea has been seized upon and elaborated by many astrobiology team members. Principally, it's worth mentioning Andre Becker and also the Caltech group, Kirschvink, Bob Kopp, Isaac Hilburn, and colleagues. Eric Gaidos, also at University of Hawaii now, was involved in this. And the best preserved Paleoproterozoic glacial deposit is arguably in South Africa, where the Makanyeni diamictite unconformably overlies roughly 2.4, although there are new dates coming out, perhaps 2.3 billion-year-old sedimentary successions, and interfingers with volcanics that have a very robust paleomagnetic signal indicating they were deposited 11 plus or minus 5 degrees paleolatitude. Immediately above the volcanics, there are reworked volcanic clasts, deposits dropstones into iron-rich sedimentary strata, which become banded iron and manganese formations, leading into a platformal carbonate succession of perhaps 2,300, although there are new toroidal zircon ages of closer to 2,200 million years for the top of the succession. And really the principal feature that the Caltech group has focused analysis on has been the banded iron and manganese formations, as shown in the Sishan and Mamatuan mines here from the Kalahari province. The idea is that the manganese especially requires oxygen, something we'll return to in a minute, but broadly speaking, this is very consistent with the general trend of mass-independent sulfur fractionation elaborated by James Farquhar and many colleagues, including Shuhei Ono, now of MIT, and most recently yesterday, Papineau et al. From the Colorado National NAI group went to the Huronian succession and essentially have pulled out a very similar story in which there's a dramatic departure from varied mass-independent isotope fractionation values to the expected oxygenic zero, essentially, cap 33 at approximately the time and in about the location stratigraphically of the Makanyeni diamictite or its presumed global correlative glaciations. The final classical evidence for oxygenation accompanying the Paleoproterozoic first major Precambrian glaciation is the appearance of these giant banded iron formations immediately after the glacial deposit, and then the disappearance shortly after during the Paleoproterozoic and Mesoproterozoic eras. Curiously, the banded iron formations reappear in the Neoproterozoic, but only in successions intimately associated with glacial deposits themselves. Here, for instance, there's a rafted carbonate dropstone in the Mackenzie Mountains of Canada, deforming banded iron formation as the Rapitan Formation in the Neoproterozoic. The question, though, is oxygen required, somehow associated with both these Neoproterozoic and Paleoproterozoic glaciations to produce the banded iron formations? Of course, there are many oxidants on an electron ladder. Here, for example, is the Gaidos et al. 1999 electrochemical ladder at approximately neutral pH, where you can see that species like uranium, which have actually relatively negative PEs here, could be oxidized if they're simply coupled biochemically to iron reduction. On the other hand, Kirschvink et al. And Kopp et al. Recently have noted that manganese oxidation, formation of manganese oxide, such as in the manganese banded iron deposits and manganese deposits on the Kalahari craton, must be coupled either to nitrate reduction or essentially presence-free oxygen. And since nitrate to be present presumably requires the presence of oxygen, this is the strongest direct consideration for presence of molecular oxygen at quantitative levels in the Paleoproterozoic atmosphere, associated with the Makanyeni glacial diamictite horizons. So let's keep holding on to this idea that Paleoproterozoic glacials, especially in South Africa at about 2,200 million years, seemingly require presence of free oxygen in the atmosphere in order to produce banded manganese deposits. Recall the character of a glaciation during its lifespan is cold and dry, and presumably leads to ever lower relative quantities of oxygen in the atmosphere, since, to some extent at least, you expect to be impeding photosynthetic production of oxygen, if it even exists to begin with, and also burial of carbon and buildup of reduced species if they're exposed periodically in small open ocean pockets will likewise tend to bury oxygen rather than produce it. So there's a cold, dry, low oxygen environment expected during glaciation. And recently, Danny Lang and colleagues at Caltech, as Carl referred to in his introduction, have noted a novel mechanism, not a novel mechanism insofar as it's been studied in many extraterrestrial analogs on Mars, for instance, on Europa, and also on the Greenland and Antarctic ice sheets, which is that photolysis of water in cold, dry, and low oxygen environments produces hydrogen peroxide. Hydrogen peroxide has a freezing point very close to that of ice, and so if it's present in sufficient quantities that it can rain out and be buried in ice before it is in turn photolized into hydroxyl radicals or else recombined with free hydrogen to form water vapor in the atmosphere, then you can preserve a very strong oxidant for geological timescales in ice, which might then melt away at the end of a Snowball Earth glaciation. This process happens today as observable in, for instance, Antarctic ice cores. Here, many authors have noted that there is a historical increase in the concentration of ozone in South Pole Antarctic ice cores, presumably related to low ozone, relating to the ozone hole, allowing greater penetration of ultraviolet light, which permits the photolysis, which enhances the photolysis of the water. And likewise, there's a seasonal cycle. You can see the scale bars here at shallow ice core depths are different, up to 200, than the scales at deep drill hole depths, reflecting this presumably anthropogenic increase in the peroxide concentration in ice. And during melting of ice sheets during the summer, much of this peroxide is released into the ocean. Lang and colleagues considered a one-dimensional model of an Archean atmosphere to start with, only containing hydrogen, molecular hydrogen, and nitrogen, but receiving constant input of carbon dioxide from volcanic outgassing. And they let that evolve, solving for mass continuity equations for 10 to 30 million years. Here's one standard result which they produced. Simulating this snowball for about 30 million years, they built up hydrogen peroxide to a mixing ratio of 10 to the minus 10, considerably more than today, at close to the surface of the Earth. Because the characteristic diffusion scale for hydrogen peroxide is approximately 1 kilometer in today's atmosphere before it becomes photolized by ultraviolet light, you have to build up the concentration not merely at altitude, but within a kilometer or even closer, preferably to the Earth's surface, in order to be buried on any ice that might be present, as in this model. Sensitivity analyses of Lang et al. Suggested that the peroxide deposition rate will increase with ever greater hydrogen escape to space, which might be modulated by things like geomagnetic field strength and other atmospheric conditions. Depressed hydrologic cycle, in other words, the more active the water cycle, the less peroxide will tend to be buried. Depressed temperature, so the colder it is, the more peroxide will be buried. And, of course, depletion of stratospheric ozone, as in the modern case in Antarctica. So given the order of magnitude variations with that sensitivity analysis, it's nonetheless certainly conceivable in a tens of millions of year hard snowball, not necessarily an impossible thing by the simple energy balance or the advanced GCMs, as we talked about early in the talk here, to produce up to 0.1 to a whole atmosphere worth of oxygen equivalent hydrogen peroxide, which would be released and turned into oxygen at the end of a snowball glaciation. The scenario that Lang et al. Hypothesized then for implications is something like this. Suppose the earliest Precambrian glaciations, such as the Pongal in South Africa, without any firm paleomagnetic evidence for low or high paleolatitude, but it seems to be probably unique, at least in the cratons that preserve rocks of that age. and also possibly the earlier of the Huronian, Hurwitz, Snowy Pass supergroup glaciations in the Paleoproterozoic that do not have evidence for low paleolatitudes, so they also might not be true whole Snowball Earth glaciations. These might have, just like the modern Antarctic scenario, produced some hydrogen peroxide in a methane atmosphere dominated Archean to early Paleoproterozoic Earth. This would be the first strong oxidant which would exert some sort of selection pressure, conceivably, driving evolution of enzymes that have to be present to deal with peroxide as a natural biochemical product of reactions such as oxygenic photosynthesis or mutation of enzymes involved in that, mutation of proteins involved in that. Oxygenic photosynthesis could be exacted only once you'd evolve these things, such as manganese catalyse or superoxide dismutase. And then an atmospheric methane reservoir could crash suddenly on the timescale of genetic population of the Earth, essentially, in bacteria, as opposed to the photo atmospheric chemical timescale of hundreds of millions of years initially proposed by Pavlov and others. This would trigger a Paleoproterozoic snowball in the classical sense of you've suddenly lowered the greenhouse forcing that the Earth is dependent upon, producing lots of peroxide in the ensuing multi-millions of years or tens of millions of years Snowball Earth, helping precipitate the Kalahari manganese eventually at the end, so you don't just need oxygen as previously supposed. Peroxide is certainly also a very capable oxidant of even generally positive EH species like manganese. And curiously, perhaps overcoming the nitrate limitation paradox to oxyatmoversion that's been enunciated by Fennell and colleagues, Astrobiology Institute members, in which they note that the very first introduction of molecular oxygen would seem to be self-limiting biospherically because many nitrogenase cofactors depend on redox-sensitive metals like, for instance, manganese. And furthermore, once you have a little bit of oxygen, you can begin doing pathways like aerobic denitrification, which would tend to nitrogen limit cyanobacteria, which are presumed to be the major likely oxygen pumpers in a post-Macaniani world, until there was sufficient oxygen to fix the nitrogen from nitrate. So it's a chicken and the egg. Given a little bit of oxygen, it seems to become more difficult to gain more oxygen. However, this sudden influx of hydrogen peroxide could overwhelm the nitrate limitation paradox and permit the oxyatmoversion, as obviously is evidenced in the geochemical and geological rock record. So much for the Paleoproterozoic. We have the Neoproterozoic, where a high methane atmosphere is no longer very tenable for the pre-snowball, say, 750 to 800 million year Earth. Is there a similar oxidation or oxygenation, and the two are somewhat distinct as we've discussed here, linked to the Neoproterozoic glacial deposits? Well, of course, there are the banded iron formations in the Sturtian, in the classic Sturtian, approximately 700 or maybe 650 million year old glacial deposits. There are other curious features of these glaciations, including cap carbonates. Here's my favorite picture of a cap carbonate from the Svalbard succession that Pippa Halverson, Adam Maloof, and colleagues have worked on, partly funded by the NAI, in which the idea of a cap carbonate is during the latest Neoproterozoic glacial deposits and at least one of the Paleoproterozoic glacial deposits, it's not clear if that one, the Bruce diamictite in the Huronian supergroup, correlates to the Macaniani demonstrably low paleolatitude glaciation or not. But in one Paleoproterozoic and many late Neoproterozoic glacial deposits, even if they're siliciclastic shale sand dominated successions during the glaciation, before the glaciation, after the glaciation, immediately on top of the glacial deposits there's a thin carbonate bed, generally of dolostone, sometimes of limestone, seeming to indicate a flux of alkalinity to the oceans overcoming siliciclastic deposition. There's also, as you can see perhaps in this picture, a characteristic reddening of carbonates and siliciclastics immediately atop the cap carbonate, leading back into, here in Svalbard, drab, dark-colored black siliciclastics of the Dracoizen formation. Classically, a similar startling cap carbonate is preserved in Newfoundland, where at approximately 581 millions of years, 3 kilometers of deep water, black, organic-rich siliciclastic turbidites became glacially supported. In other words, there are striate class and drop stones introduced into the turbidites. And then there's a very thin, 75 centimeter or thinner, here in this section on Little Colonnet Island, only 10 centimeters thick, cap dolostone immediately above the topmost glacial deposits. And it goes into, younging to the left in the picture here, although it's not as evidenced from the outcrop weathering, a red fine grain sequence, so a reddened interval, just like the previous picture from Svalbard, before returning to a full 5 kilometers of organic-rich turbidites, just like before the glaciation. So at 581 million years, there's a glaciation called Gaskiers that shows the same classic Marinoan reddening, which is somewhat like, reminiscent of the oxidation-oxygenation banded iron formation association of the Paleoproterozoic. There are no airtight paleomagnetic results from Gaskiers, and it's not clear if this is a true Snowball Earth or if this is right on the road between the Neoproterozoic, Paleoproterozoic low-latitude glaciations and the Ordovician, Permian, Plio-Pleistocene, moderate paleolatitude glaciations, as I talked about early in the talk. Recently, Canfield and colleagues have performed a method which they term highly reactive iron ratios, which essentially is a measure of the fraction of iron in rock which is bound up in siliciclastic debris, unreactive clays and silicates, as opposed to all other forms, sulfides, carbonates, oxides, and so forth. And the idea is, in modern settings that are well understood geochemically, like the Black Sea, this ratio is relatively sensitive to the oxidation state and oxygenation of the seawater. And they see, to first order, a step function decrease of their iron highly reactive to iron total. This is another way of expressing this fraction of siliciclastic bearing iron at the very top or between their topmost Gaskiers sample and their lowermost super Gaskiers deep water organic rich turbidites. They suggest this indicates there was at least some oxygenation quantifiably accompanying the deglaciation of the Gaskiers event. They also go on to present an order of magnitude argument for what everyone has assumed is the case, which is that the ensuing evolution of complex macrobiota, the Ediacarofauna, and of course the later Cambrian explosion, would seem to require greater oxygen levels than are assumed to be present in the preceding parts of the Neoproterozoic in order to permit surface area to volume sort of considerations for building complex body plans. The evidence for low Neoproterozoic glaciation is dominantly coming from work of Matt Hurtgen and colleagues recently. Matt Hurtgen is now at Northwestern University, who study carbonate-associated sulfate sulfur isotopes, which indicate very low sulfate concentrations in Neoproterozoic seawater, inferring then low oxygen concentrations in the overlying atmosphere. This is the Gaskiers event is one of, as originally I noted on one of the early slides, many Neoproterozoic glaciations, of which all workers tend to agree at least 3 exist, so-called, in this compilation by Halverson et al. And colleagues, supported by the NAI. And this diagram has been somewhat modified for a particular correlation of this part of the blue Namibian and Svalbard curves to actually precede the Sturdian glaciation. However, the whole character of the idea of the swings of carbon does not change, nor actually the substantial correlation of the successions, and that's been modified in Halverson 2007 recently. There are at least 3 glaciations called Sturdian, Marinoan, and here Varanger, which is presumed to be equivalent to the Gaskiers event we just talked about. Note that all 3 are associated with quite severe negative carbonate-carbon isotope excursions beforehand. Here, this event is considered the Wanaka Johnny/Shuram anomaly for 3 different locations where it's inferred to be present by global correlation, which is not airtight, but is certainly plausible. And there are various other features of returning positive excursions after each of these glaciations that might be related to things like oxidation and oxygenation of the ocean. In particular, the Wanaka-Shuram anomaly associated with this Gaskiers glaciation we've just talked about has been documented in more than 30 outcrop sections with extensive sequence stratigraphy done by Erwan Legeroux and colleagues, formerly at ETH Zurich, now at University of California, Riverside, in which there's a decrease in carbonate carbon isotopes by up to 14 per mil, an extraordinary number, reaching a nadir of negative 12 per mil, far below the expected mantle value of approximately negative 6. This would seem to indicate introduction of a major organic carbon reservoir into the ocean, overwhelming the total size of the inorganic carbonate reservoir. David Fike and colleagues have recently produced a really extraordinary data set which speaks with great detail to what's hinted at as a specific Gaskiers event, but spanning the entire, or almost the entire, Ediacaran period, using drill core from Oman, the subsurface of the same area where Erwan Legeroux and colleagues have done their outcrop mapping of the Shuram sequence stratigraphic carbon isotope anomaly. Here, in drill core, David Fike, who just got his PhD at MIT and Caltech, has produced inorganic carbon isotopes, organic carbon isotopes, sulfate sulfur, sulfide sulfur, and here he's plotting the difference between sulfate and coexisting sulfide sulfur for a great many points throughout the Ediacaran period. And there are dates from this succession of approximately 635 million years. Actually, I mean approximately. It's a very precise age at 635. I don't remember 0.5 million years at the top of the glacial diamictite, and there's a detrital zircon of approximately 621 million years in the upper Kufi formation, and then other uranium-lead zircon ages from ashes in the Bua of approximately 550 million years. Fike et al. Prefer to consider the Shuram isotope excursion. Here, this decrease in inorganic carbon essentially decoupled from organic carbon isotopes, although certainly there's some change, but in an opposite direction, to be related to a 580 million year Gaskiers event. This is plausible, though not required from the age constraints from the direct section, a point I'll return to later in the talk. Fike et al. Suggests there are 3 stages of pan-Ediacaran oxidation of the Earth's ocean and atmospheric reservoirs. In the first, predominantly indicated by the increase in delta 34S, the difference between del 34S of pyrite and sulfate coexisting, this would seem to indicate growth of a sulfate reservoir in the ocean, which is different than the Hurtgen et al. CAS low sulfate values inferred for all previous rocks. During step 2 of the oxidation event, the inorganic and organic reservoirs become decoupled. There's quick oxidation of a deep DOC reservoir, similar to what's inferred by the somewhat quicker, apparently, although it certainly is the same event, Shuram anomaly records from the outcrop of Legeroux and colleagues. And in step 3, bacterial sulfur disproportion further increases the cap delta 34S to values of almost 50 per mil at various parts of the Ediacaran and into the Cambrian. The question is, do any of these events directly relate to Gaskiers glaciation? And if so, what is the time scale of Gaskiers deglaciation and presumed oxygenic increase? As Fike et al. Note, this stage 1 oxidation seemingly occurred over 25 million years after the Marinoan demonstrably low paleolatitude glaciation. So here, the sulfate increase, which is presumed to relate to ever-increasing delta 34S values, spans the entire range of hundreds of meters of stratigraphy up into the 621 million year detrital zircon stratum. So it's not as seemingly quick as the Gaskiers' putatively Shurram event is hypothesized to be. Dan Condon and colleagues have noted that, strictly speaking, the Shurram anomaly is quite undated anywhere between 632 million years in China, with carbonate carbon isotope values in green here, and approximately 551 million years where they see the Shurram anomaly is already on its way back toward positive values. Here, Condon and colleagues prefer to incorporate radiometric ages of theirs from Newfoundland, the Gaskiers event, at this point in the stratigraphy, partly based on paleontological and partly based on base and substance analyses, but there's a great deal of wiggle room. And so the point here is, even though Fike and Legaroux and colleagues would tend to think that this Shurram anomaly, Shurram-Wannock anomaly, belongs down here at Gaskiers glaciation, at the furthest end member, it might be close to 560 million years. And in principle, it could even be older than 580 million years. So there's a lot of uncertainty in the age of the Wannock-Shurram anomaly and its direct correlation into any Gaskiers glaciation, since in the Gaskiers type section there are no carbonates except for the cap carbonate. This is the end of part one of my talk, and so I want to reiterate the exciting work that's been produced by these really extensive data sets by David Fike, Erwan Legaroux, Danny Lang, and colleagues, which is there's convincing association between glaciations and oxidation events. The most convincing, Paleoproterozoic Snowball Earth glaciation, the Makanyeni Formation in South Africa, may have been caused by and in turn caused dramatic oxyatmoversion. And Bob Kopp and colleagues at Caltech have been out front in enumerating these hypotheses. And this leaves the question, which I'm going to address in part two of my talk, just how similar is the Paleoproterozoic and the Neoproterozoic case, and if the Paleoproterozoic snowball was associated with first-order oxyatmoversion, what causes a Neoproterozoic snowball Earth? So recall from earlier slides, the approximate timescales for entry and exit from glaciation are extremely quick, based, if nothing else, on physics of how ice is expected to melt, and ice sheets are expected not to stay in limbo between glacial and an interglacial state. There are other reasons also to suggest that deglaciation has been very rapid, which I'll get to in a minute. Recall also from Halverson et al.'s carbon synthesis that immediately above the Marinoan glaciation there is, and possibly above the Sturtian glaciation, although this part of the curve has been modified by Halverson in 2007, there's a dramatic negative carbon isotope excursion which happens in short scant meters, presumed to relate to catastrophic silicate weathering and Rayleigh distillation of the carbon dioxide greenhouse atmosphere that had built up over the snowball. And recall again, the cap carbonates often have unusual features for the successions they're within, associated with reddening, the anomalous isotopes I just talked about, and various other features, such as giant wave ripples. And this is a point which is difficult to overemphasize if you've been in the field and seen some of the structures in cap carbonates. Any geologist who comes and works on cap carbonates sees textures which are unprecedented in the rest of the which are together unprecedented throughout the Precambrian or Phanerozoic record. Individual members like sheet cracks, seeming methane seeps, stromatolites, negative carbon isotopes are seen in different places, but all together they're present immediately above the Marinoan Neoproterozoic glaciation. And at decimeter or even meter scale, there are sharp-crested depositional carbonate antiforms that seemingly have crests which migrate back and forth just like a very small-scale wave ripple in a fast flow regime. Allen and Hoffman suggest this was produced by sustained gale force winds on a time scale of days, hours, years, decades, suggesting that the whole deposition of cap carbonate was a similarly very quick event. Geochemical modeling also suggests the deposition of the cap carbonate occurred on a time scale of, say, 2,000 years plus or minus an order of magnitude. There are other features like upward-growing sediment-draped seafloor crystal fans, which presumably had to outpace sedimentary detrital input, and other, perhaps more modelly dependent evidences, lines of argument, to suggest that the cap carbonate sequence, that anomalous carbonate bit above the Slisk-classic Neoproterozoic snowball Earths, was very rapidly deposited. There have been two fascinating recent tests of this and related expectations of the hard Neoproterozoic snowball Earth hypothesis. The first testament is to a prolonged sea ice cover, and it comes from Central Africa's Lufilian Arc, where drill core in Congo and Zambia of two successions presumed to correlate to the Sturtian and the Marinoan glaciations, the older and the younger, although the truth may be more complicated than that, Neoproterozoic glaciations, shows dramatic iridium concentration and extraterrestrial iridium ratio profiles in claystone immediately below the Marinoan correlative cap carbonate and throughout decimeters of the lowermost Sturtian calcareous shale immediately above glacial deposits. So the deglacial aftermath of glaciations in Central Africa produced these shocking extraterrestrial iridium anomalies. Assuming these were carried by interplanetary dust particles as opposed to major impacts, this implies a time scale for accumulating iridium on the continents, then washing them into the ocean afterwards, of something like 12 million years, or at quickest, assuming an Ordovician IRD flux, say 3 million years for the duration of snowball Earth glaciation. Testament to the ultra-greenhouse escape seems to be supported by incredibly precise trace isotopic analyses of cap dolostone from Namibia. In this case, the presumed Marinoan equivalent, 636 million-year-old cap dolostone of the Kyleberg and Myberg formations, in which trace concentrations of boron substituted for carbonate in the carbonate lattice show a negative excursion of -9 per mil over 2.5 meters in the cap dolostone before returning to their value over hundreds of meters of the ensuing cap limestone. There's also a decrease in calcium isotope composition, suggesting together that pH of the oceans might have dramatically acidified, since fractionation of boron depends on the speciation of borate and its associated complexes in seawater, which is itself pH dependent, among other things. And calcium isotope compositions are presumed to change only if you change the residence time of calcium by increasing the weathering rate from the continents or slowing down the sedimentary burial of calcium in the ocean. Because cap carbonates are presumed to be fast deposited, this indicates, or this is hypothesized to indicate, it was interpreted to indicate, an increase in silicate weathering concomitant with ultra-greenhouse high CO2 acidification of the ocean in the immediate aftermath of the Neoproterozoic snowball. However, and this gets to my particular area's interest, there have been 3 previous paleomagnetic studies that show apparent geomagnetic reversals within Marinoan equivalent cap carbonate deposits. First, Lee et al. In Western Australia in 2001, then Ricardo Trindade and colleagues in Brazil, and Ben Kilner and colleagues from the UK working in Omani successions have each documented at least one apparent geomagnetic reversal in a cap carbonate, but none of the studies are airtight for reasons not necessarily of the author's doing, but because of outcrop limitations and such. So the question is, first, are these indications reliable? And second, what is the implication? Through the last 180 million years, geomagnetic reversals happen, say, on tens to hundreds of thousands or even millions of years time scale. If there's a geomagnetic reversal in the cap carbonate, does this mean it took millions of years to deposit? Well, at quickest, in the Hatangian epoch of the Jurassic, there were up to 20 geomagnetic reversals in approximately a 1 million year ammonite biozone. So at quickest, geomagnetic reversals might happen at 20,000 to 50,000 year time scales, but this is still much greater than the 10,000 year geochemical modeling or the extreme rapid deposition rate seemingly indicated by the climbing wave ripples for the hard snowball Earth scenario cap dolostones. So my investigation addresses these points. And the thing to remember about the Earth's geomagnetic field is it reverses episodically, unpredictably. The inclination of the field varies as a function of latitude, from nearly flat with respect to Earth's surface at the equator to nearly vertical at the pole. And if averaged over a time span of 2,000 years, the location of the apparent geomagnetic pole approximates, on average, the true geocentric axial dipole. In South Australia, Neoprozoic strata are exposed in an open fold belt in which the central area is least metamorphosed. There are other correlative basins throughout Australia, and these have been many of the locations where the Snowball Earth hypothesis for the Neoprozoic has been first elaborated by Australian Geological Survey colleagues. Classically, in the 1980s, fold tests in which magnetization was shown to wrap about bent bedding, assumed to be related to sedimentary seismic deformation, within a rhythmite member resembling glacial varvites in the Alatina Formation of South Australia, was shown to have flat magnetization with respect to bedding, suggesting it was formed at the equator. Many authors have replicated this study, and others have considered it, suggesting that because varvites might be very quickly deposited, say 60 to 20,000 years total for only 10 meters of monthly couplets, that you might only be seeing a very strange excursional direction of Earth's magnetic field. Therefore, the Neoprozoic glaciations might not truly be low latitude. Linda Soul and colleagues at Columbia University addressed this in 1999, where they measured systematic paleomagnetic analyses throughout sandstone and shale and glacial diamictite intervals in 3 different sections, essentially producing a nearly replicatable magnetic polarity stratigraphy, also of low paleolatitude. So the Alatina glaciation, age unknown, but presumed to correlate to the 635 million year glaciations, is clearly at low paleolatitude in late Neoproterozoic time. Say 7 degrees paleolatitude is a good estimate. I went to 3 sections within the central undeformed part of the Flinders Ranges of South Australia, where the Alatina Formation, here in this dark brown color, is preserved especially well in the flanks of a salt diapir, active during Neoproterozoic time, and a 4th section in the same outcrop belt. Here, 8 kilometers separates Alatina Creek from Trezona with the recently ratified GSSP for the Ediacaran period at Enorama Creek in the middle. And there's another section in the same outcrop belt 15 kilometers north of Parachilna Gorge. This is what the rock looks like. Here are glacial diamictites of Alatina Formation. They're red beds. Oh my goodness, I have no idea. Okay, here we're back. Okay, here's an incisive red channelized sheet sandstone leading to mixed siliciclastic carbonate deposition showing conformable gradual increase in carbonate content until you reach the 6-meter thick cap dolostone at Alatina Creek. The cap dolostone shows the characteristic negative carbon isotope anomaly and these unusual climbing wave ripples. Rock magnetics shows that there are abundant iron oxide particles. These are likely sourced from adjacent banded iron formations of Paleoproterozoic age on the adjacent cratons. They're associated with clay, and so the magnetism of this rock is presumably a detrital, little grains of ferromagnetic hematite, antiferromagnetic hematite rolling into the basin and aligning on average with Earth's magnetic field at the time of deposition, cemented into place by the carbonate. The magnetic records through the 6 meters or so of cap carbonate at Alatina Creek are as follows. There is a switch, not shown in this particular diagram, from the conformable siliciclastics of the uppermost Alatina Formation into the base of the cap dolostone, which has a certain magnetic polarity. Here we're showing the latitude and the longitude, respectively, of the computed geomagnetic pole, because its 2-dimensional projection is a non-unique way of looking at changes. And then there's a polarity switch about midway through the cap carbonate over an interval of only about 13 centimeters, and the rest of the cap carbonate into the mixed transition with overlying siliciclastics is of the other polarity. Black and white represent, for instance, normal and reverse polarities. Their choice is somewhat arbitrary. And then there's another reversal back to normal polarity, arbitrary, within the mixed transition into Brachina Formation siliciclastics. Here are locations of the giant wave ripples seemingly indicating fast deposition of the cap carbonate. The same pattern holds at the Enorama Creek GSSP, in which the upper part of the Latina Formation is reversely magnetized, the lower half of Cap Dolostone is normally magnetized, the upper half of Cap Dolostone into branchless siliciclastics, not cropping out well here, is reversely magnetized, and there's yet another reversal within the mixed transition to overlying monotonic siliciclastics. This is even true 8 kilometers north of Latina Creek at Trezonabor, where the cap carbonate has been attenuated to only 1/10 of its thickness. Here, the cap carbonate is only 75 centimeters thick, and yet again, the uppermost Latina diamictite and sandstone facies are normally magnetized. An unconformable surface and sandstone associated with it locally at Trezonabor is reversely magnetized. The bottom part of the cap carbonate is normally magnetized, and then there's a transition into reverse polarity over at least one sample here, and you see stable reverse polarity for about 6 samples within the very top 10 or so most centimeters of the 75 centimeter thick cap dolostone at Trezonabor. Altogether, you might stretch these different thickness sections at Latina Creek, Enorama Creek, and Trezonabor and produce a composite magnetostratigraphy like this, different sections in different colors with 1 meter stretching factors shown for scale over here. The point is there's a geologically, stratigraphically coherent system to the magnetic polarity switch within Cap Dolostone that seems to validate the previous studies, suggesting there really is a paleomagnetic signal switch within the Cap Dolostone. And in fact, there are 3 geomagnetic polarity switches associated with Cap Dolostone. This one just below it, this one just above solid Cap Dolostone. So we need to ask now, are these truly geomagnetic reversals of a normal geodynamo in which one of these polarity zones is tens or hundreds or millions, well, tens or hundreds of thousands or millions of years, and can we do a more precise job of quantifying deposition rate? Here's the example showing that reversal rate is very uncertain. However, the last 3 geomagnetic reversals, when studied in very high deposition rate ODP, IODP cores that have age models independently derived from radiometric isotopes, show an interesting latitude dependence from sites near the equator to sites at about 70 degrees latitude north or south of the time it takes the geomagnetic field to switch from one polarity to the other. So it might switch erratically every 100,000 years, but the amount of time it takes is perhaps expected to be relatively constant between, say, 10,000 at most and 2,000 years at least, with systematics for the latitude of the site which is observing that switch. We'll return and apply that to the Cap Dolostone in a second. Addressing whether these are true geomagnetic reversals, there are things called geomagnetic excursions. So here, example, is Jim Chandler's calculation of the last 2.5 million years from similar high deposition rate ODP, IODP cores in which within stable polarity zones, here's entirely normal polarity zone, they're very short, say 1 to 2,000 year duration spikes where the geomagnetic field suddenly switches polarity before returning back to its generally long-term stable configuration. The question is this an excursion? Is this an excursion, in which case we only have 1 or 2,000 years, 1 or 2,000 years, somewhat more in line with the fast deposition expectation? I would argue that it doesn't seem to be the case. For one thing, there's adjacent repetition of events. There's one paleomagnetic reversal in the cap carbonate going from white, reverse polarity, to black, white to black. A second reversal and a third reversal at approximately equivalent intervals. This is different from the recent record in which you have these very short excursions occupying otherwise long-term, relative to the time span of the excursion, stable polarity crimes. Secondly, there are many reversals that everyone accepts are true geomagnetic reversals in the overlying branchless siliciclastics and in the Latina Formation itself. It's somewhat arbitrary to consider those reversals and these excursions. We probably have to say everything is very quick, unexpected switching the magnetic field, or everything is standard uniformitarian geomagnetics. And third, there is fine structure within these polarity zones. For example, in the different sections, there are between 7 and sometimes 1 samples recording transitional directions between one polarity state and the other in the middle of the cap carbonate. Likewise, you might squint and say there's a transition between polarities at the top of the cap carbonate, at the bottom, and there are even individual samples, or sometimes 2 or 3 samples here, that seem to excurse from the average direction of one of the polarity crons to, arguably, here is an excursional direction. In that case, this interval of 10 centimeters is something like 1 to 2,000 years, and this whole interval is something like 10 to 20 or 30,000 years. Curiously, in the best of the 3 other paleomagnetic studies for stratigraphic high resolution, that of Ricardo Trindade and colleagues in Mirassol de West Cap Carbonate, Brazil, their pattern is somewhat similar to that found in the presumed correlative Knucklina Cap Dolostone. They have one polarity, which they denote as reversed, arbitrary, in the bottom of the cap dolostone, switching to another in the middle, switching back to a polarity in the top, and then they have very short 1 or 2 sample departures from the topmost polarity cron superimposed on that. This is somewhat similar to one polarity zone, then the other polarity, then the other, with some short departures in the Knucklina Cap Dolostone I've been studying. So if you accept the uniformitarian interpretation and say the cap dolostone took tens of thousands of years to deposit, how do you get around the giant wave ripples? You probably have to appeal to non-uniformitarian sedimentology, microbial binding of non-horizontal surfaces, building non-linearities and subsequent depositional events, etc. I don't have an answer for the crystal fans, but nor are crystal fans present in Knucklina or Mirassol Cap Dolostone. So we haven't directly constrained the deposition rate of those. The other parameters, such as the boron...
Tim, excuse me, we're running kind of long, and so I was wondering, can you finish up in within about 5 to 10 minutes so that we can have time for questions?
Yep, no problem. 5 minutes or so. The carbon, boron, and iridium profile anomalies are to some extent model dependent. For example, the calcium isotope anomaly that accompanied the boron anomaly could be due to, as interpreted, the enhanced silicate weathering, or it could be a result as slowed calcium burial, as might be expected in slow deposition rate cap carbonates. In terms of presumed glacial eustic transgressive affinity, there really is no easy way, as I understand it, for general circulation models to prolong a deglaciation for hundreds of thousands of years. We would seem to need to invoke unexpected negative feedbacks like fog bank cover or things like that to slow down the greenhouse forcing in the aftermath of a Neoprozoic snowball Earth. The final part of the story is the Knucklina cap carbonate paleolatitude is considerably higher than that of a latina formation. Here, the varvate latitude was equatorial. The sandstone-siltstone latitude was somewhat higher, 7 degrees, but Knucklina cap carbonate latitude on an inclination equal area diagram is closer to 20 degrees paleolatitude. The pole position in blue is superimposed on other poles from Australia that show the final mysterious, possibly non-uniformitarian aspect of Precambrian time, dramatic dispersion of seemingly robust paleomagnetic poles. In this case, the oldest of these Australian poles, which are listed here but aren't important for the purposes of this talk, is at the tail of this arrow, leading in mid-Ediacaran time to Bunyuru Formation at the tip of the arrow. Then it returns to Upper Perditatica Formation in still younger Ediacaran time over this tail-to-tip arrow, returning to a moderate relative position in this pole swath in early Cambrian time and continuing on to a dramatically different late Cambrian apparent polar wander position. This would seem to indicate, since the North Pole is presumed to always stay at the North Geomagnetic Pole, that in fact Australia is rotating by about 90 degrees back and forth on a very quick millions of years timescale. Australia isn't the only continent that shows this pattern. The best constrained global paleomagnetic database for the Ediacaran period comes from Laurentia, ancestral North America, where all possibly putatively primary paleomagnetic poles are plotted in blue here, the most reliable in dark blue. If you sort these by age, here's a scale from purple to light purple, blue to green. The oldest is here, long-range dikes at 615 million years, excursioning to poleward apparent polar wander locations, coming back to equatorial positions, back to polar, back to equatorial in blue, back to mid-latitude, and back to equatorial. Laurentia, in this case, is moving from the equator to the pole, equator to the pole, the equator to the pole, and back again, as many as 6 times in a standard paleomagnetic interpretation. The non-standard interpretation is that this represents true polar wander. If you imagine bugs crawling on a surface of a beach ball, the beach ball will start rolling. Likewise, mass anomalies imposed on the surface of a planet or within the interior will tend to change the spin dynamics of that planet. For example, the greatest gravity anomaly in the solar system, the Tharsis volcanic province on Mars, is located precisely on the Martian equator, possibly as a result of previous true polar wander. When we go back to the glaciations, which are associated with these carbon isotope records in the Ediacaran, besides the sturdy Marinoan and Bowring or Gaskiers glaciation, the other dramatic carbon isotope event is this Bitter Springs stage at about 800 million years. The final recent exciting study that's come out relating to this problem is that by Maloof and colleagues at Princeton, in which they went and studied carbonate platform successions of Svalbard, including sequence boundary unconformities of unaccounted for duration. And they found that the carbon isotope signal here in black excurses dramatically across the sequence boundaries in concert with the paleomagnetic signal in green. Note, a 180-degree switch in polarity, in magnetic polarity would only move this to about this location, whereas the true difference in paleomagnetic declination is something like 60 or 70 degrees. So there seems to be this dramatic change in apparent polar wander coincident with carbon isotope switching. This is suggested on this pole diagram, and the paleomagnetic result is very highly robust since it's constrained by a syn-sedimentary fold test where magnetization clusters more coherently when the fold is unfolded versus when it's folded. This is a true 800 million year old remnant direction. It also indicates paleoenvironmental things like moving Australia into and out of evaporate belts, which are consistent with the geological and stratigraphic record of those basins, hence the term Bitter Springs stage for the Bitter Springs evaporites. And Maloof et al. Model that the difference carbon isotopes is due to sea level fluctuations exposing and introducing different reservoirs of organic versus inorganic carbon. If you modulate the fraction of organic carbon burial from about 20 to 40%, you could easily produce the -5 per mil shift and then +5 return of the Bitter Springs isotope stage, here and here, before and after the 2 true polar wander events. So the final thing that is worth saying is that's at 800 million years, but this database suggesting the 6 times polar wander switching of North America is entirely Ediacaran, synchronous with Gaskiers glaciation, or spanning the same interval, and possibly Marinoan glaciation. Perhaps a great many of these carbon isotope anomalies, just like Bitter Springs stage, are driven by true polar wander, and this is what drives glaciation by changing global carbon cycling in the Neoproterozoic, just as oxyatmoversion may have driven it in the Paleoproterozoic. If these problems are ever to be resolved, we need new radiometric ages, still more integrated chemostratigraphic data sets to ever more calibrate the successions, and more paleomagnetic measurements to test whether true polar wander is truly the explanation for these strange signals. The final thing to note is that the alternative to true polar wander is non-dipole geomagnetic fields, which would cast aspersion on everything, including the basic latitude of paleomagnetic determinations from Snowball Earth deposits to begin with. So no matter what we face, astrobiologists in the Precambrian are forced to reconcile themselves with seemingly very non-uniformitarian processes and outcomes. Thanks.
Tim, thank you very much. It was an information-loaded presentation. I must apologize. We had some WebEx problems along the way, and there were at least a couple of slides that we didn't see clearly here. I think that was probably true across the net. So, Tim, could you just mute your mic for a second? I think that's probably where the feedback's coming from. Or is it coming on our end?
Muted.
Thank you. Can you all hear me now? What's our status, Marco?
I can hear you.
Okay.
We can hear you.
Okay, I think we may have had the feedback on our end, but we've got it fixed. I was going to ask one quick question, but let me see if anybody has raised their hands on...
No.
Okay. First of all, we invite you to ask some questions. I will start off by asking just one question about one detail early in your talk that I didn't quite follow. You pointed to an iridium anomaly that was due, you said, to extraterrestrial dust infall. It wasn't quite clear why that showed up as a spike, if this is continuous extraterrestrial dust entry into the atmosphere. Could you explain that particular point?
The idea of Bowring et al. Is it would show up as a spike only in something approximating a hard snowball state, where you're segregating the interplanetary dust reservoir, which is accumulating on top of the ice or on elevated highlands, from the basins in which the sediment is deglacially preserved. So in other words, if there's a soft snowball, you wouldn't see a spike. Continuous IDP flux would just continuously be preserved. On the other hand, in a hard snowball, you'd build it up, and the concentration would be related to the amount of time, which is what they modeled.
Gotcha. Thank you very much.
No other questions?
We encourage you to raise your hand on WebEx to ask questions.
Can we just go around, maybe to Ames? No reason to put them on the spot.
Are there any further questions for Tim?
If not, thanks for listening.
Well, Tim, thank you very much. We appreciate that. And we just have a question from Indiana.
Hi, Darius from Indiana. I had actually two questions. First was, I didn't quite understand what was the effect of polar wander on the carbon isotopes in the sediments. So that's one. And another one is, you said that the switching of the orientation of the poles from north to south and south to north takes about 2,000 years from 1 to about 10,000 years, the switching period. So how would that period affect the biota living on the surface? Is it any effect on the UV radiation affecting the life on the surface to more extent during that switching period? Thank you.
The answer to the second question is quickly dealt with, and I'll be brief on the first two. Yes, during a switch from one polarity state to the other, the geomagnetic field strength does go down in all observed Phanerozoic records. Presumably that allows greater penetration of ultraviolet light, leading to more mutations and so forth. But whether that has any cumulative effect on biota is really uncertain. And certainly at this stage, most of the biota are marine microorganisms, in which case the penetration of ultraviolet light into seawater is somewhat different than, say, a land-based organism would be. In terms of true polar wandering carbon isotopes, because Earth is not perfectly solid, it's viscous inside. As it spins, there's a spin bulge, and because angular momentum must always be conserved during true polar wander, which is basically slip of the whole solid Earth, the mantle and crust, on top of the core mantle boundary. So it's slip on that core mantle boundary. The Earth is still spinning in the same way it was before true polar wander ever happened. What that means is the spin bulge that used to be on the equator slips on the core mantle boundary and tends to itinerantly no longer be equatorial. So the mantle flows and relaxes to create the spin bulge once more equatorial. Because water is so much less viscous than mantle material, the oceans can adjust to the spin bulge moving itinerantly much quicker than the mantle can. Hence, during true polar wander, you see regression in two quadrants of the Earth, two opposite quadrants, here and here, and you see transgression in the other two quadrants of the Earth, those that the spin bulge is moving away from. So the spin bulge moves toward a quadrant, you get sea level drop, away from it, sea level rise. The idea is sea level drop and rise of 100-meter scale will tend to destabilize methane clathrates that are on the shelf. It'll expose previously buried organic carbon to remineralization. It might change the riverine and atmospheric circulation and rain patterns so that you're bringing nutrients to different ocean basins and you're changing carbon burial systematics. It could modulate a whole variety of carbon cycle systematics. And so Maloof et al. Simply note that the magnitude of change it would take would be 20% change in fraction of organic carbon burial. They don't say precisely where that enhanced carbon burial would be, but it's presumably related to sea level changes.
Thank you.
Thanks.
We have a question of Goddard. Goddard, would you go ahead, please?
Now? Hello?
Yeah, we can hear you now.
Okay, this is Mike Muma. Would you tell us a little more about why you think that a polarity reversal could influence biota on Earth? I realize that the lack of magnetic field permits the solar wind to penetrate into the upper atmosphere, but it's not clear to me why that would causally affect life at the surface of the Earth or below. And in particular, in order to change the UV flux at the surface of the Earth, you have to change the ozone column density in the stratosphere. So perhaps you could clarify how that changes as a result of the reduction in Earth magnetic field strength.
Well, I've slightly miscommunicated. I quite agree with you. I don't expect geomagnetic field transitions to have any measurable effect on biota. If they did, it would presumably be a response to decreased geomagnetic intensity, and you would be limited to modeling precisely the processes you just enumerated. But in any sort of sense where that leaves a record, most geomagnetists consider it quite unlikely.
Yeah, actually, that's what I was hoping you would say. It turns out that I've been sitting here thinking about the physics, and one of the things that might happen as a result of the reduction of field intensity is the solar wind then does strike the upper atmosphere, and what that does is it creates a much more intense X-ray flux. This is actually observed at Mars, for example. And the X-rays have the property that they can penetrate about 10 grams per square centimeter of material until they interact and produce a 10 kilovolt photoelectron. That happens to occur at Earth's stratospheric level. And that's just where the ozone layer resides, and so it seems to me that it's worth looking at the prospect of whether, in fact, this changed infusion of energetic electrons could, in fact, affect the ozone column density, and thereby UV
or
of the Earth.
or more generally, solar wind sputtering of molecules that react in the ozone reaction series. But I agree. What you said is the sort of mechanism you would have to pursue if you wanted to construct that sort of thing. But I don't think it's very relevant to Neoproterozoic or Paleoproterozoic biota, although in a general sense, it's a question that people always ask when you talk about geomagnetic reversals.
Yeah, I don't think anybody's thought about this particular mechanism. Well, thanks a lot.
Interesting. Thanks. I might email you about that.
All right.
Okay, it sounds like there are no further questions. Going once, going twice. Well, in that case, Tim, thank you for a very information-rich and interesting seminar, and we will see you all in about a month from now. Bye-bye.
Thanks very much, Carl. Appreciate it.